Yeah, hello everyone. Yeah, my name is Bianca Kern. I'm working together with Nadja Oneshko, Ludger Lohaus, and Michael Heist at the Institute of Building Material Science at the Leibniz University in Hanover. And I'm looking forward to present my research on the topic long-term strain development of concrete subjected to creep and cyclic loading. Let's turn first of all to the motivation of my research topic. During the service life of concrete structures, there are strain development that is predicted by creep models such as model code, ACI, or model V4. These models are usually based on investigations with constant creep stresses. Varying stresses over time are only insufficiently considered. Even though in reality there aren't only constant creep loads, the real loads are consisting of superimposed creep and cyclic loads, for example, traffic loads on bridges. And that's a problem because it's supposed that the superposition of these load types causes that the measured deformations of various reinforced concrete and pre-stressed concrete bridges exceed values predicted by creep models. In conclusion, it can be said that long-term deformation behavior due to superimposed creep and cyclic loading is only poorly investigated and understood in literature, and therefore there is a gap between the current practice and reality, which can lead to serious damage and safety risks. For modeling the strains due to cyclic loading, there are different models given by literature. Hereinafter, I'd like to focus on the model given by FRB Model Code 2010. For maximum stresses below 60% of the characteristic compressive strength and mean stresses below 50% of it, the FIB Model Code 2010 describes the total strain due to cyclic loading as elastic strain due to maximum stress, and in addition, the time-dependent viscous strain due to mean stress, whereby this part of the equation corresponds to the creep equation for constant stresses. In other words, it is assumed that in comparison to creep at mean stress, in addition to the higher elastic deformations, no further deformations occur as a result of the cyclic loading. The experimental program is intended to investigate the comparability of strains due to creep and cyclic loading and the applicability of the equations shown before. All investigations were carried out on a normal strength concrete. The creep and cyclic tests were conducted on cylindrical specimens with a height of 180 mm and a diameter of 60 mm. The storage condition chosen ensured a constant pore moisture content of approximately 100%. All tests were conducted using a specimen with a minimum concrete age of 180 days to ensure an almost complete hydration and avoid additional hardening of the concrete during testing. The specimens were tested in a sealed state to prevent drying, shrinkage, and creep. The test program is given in the table here in the middle. The compressive strength of the concrete was determined force-controlled immediately before testing using 3 cylindrical specimens of the same batch with the same dimensions and moistures as those used in the creep and cyclic loading test. The reference strength was calculated as a mean value and used for the determination of the stress levels shown here. The stress levels were held constant within the cyclic and the creep test. The maximum stress level here and here was varied, while the minimum stress level of 5% were identical in both tests. The changing of the maximum stress level causes also an increase of the mean stress level, with the aim to investigate the influence of the load type and the applicability of the presented model, creep tests were carried out with static creep stress level as creep is same as max, shown here in yellow and in dark blue. And also static creep tests with a creep stress level is same as mean were carried out, here shown in red and in the light blue. Within all tests, the experimental setup looked like the one shown here. The cylindrical specimen were sealed with an aluminum-coated butyl tape for constant pore moisture during testing. The axial deformations of the specimen were measured continuously throughout the entire test using 3 linear variable differential transformers positioned around the specimen axis at angles of 0, 120, and 240 degree. In addition, the actual force and the axial stroke of the actuator and the emission temperature, as well as the temperature on top of the loading plate, were measured and recorded. This leads me to my experimental results. Here you can see the total strain due to a cyclic test with a test frequency of 0.1 Hz. The maximum stress of 35%, the mean stress of 20%, and the minimum stress level of 5%. The sinusoidal stress leads to a sinusoidal strain curve. In the selected type of data presentation, the strains at maximum stress, mean stress, and minimum stress are displayed by the blue curves. For the stresses in between these curves, the strains are marked as the blue area. The total strain due to a constant creep stress of 20%, so equal to the mean stress level of cyclic loading, is marked in red. And the total strain due to a constant creep stress of 35%, so equal to the maximum stress level of the cyclic loading, is marked in yellow. Now it can be said that the blue area is somehow on or in between the red and the yellow curve, but the applicability of the presented model to the shown results is rather difficult in this form. Therefore, only the time-dependent viscous strains are shown in the following diagrams on the next slide. These are the strains that occur in addition to the elastic strains after the initial application of the defined stress level, often also called creep strains. For the cyclic test, the strains are shown at maximum stress, subtracting the initial strain. At this point, it must be mentioned that the differences between the viscous curves of X max, S mean, and S min are very small because, as it can be here seen, the curves of the total strains have a constant distance to each other. So now you can see here the viscous part of the previously shown total strain curves. So the remaining strain component after subtracting the elastic strain component. The viscous cyclic strain is again marked in blue, and the creep strains in red and in yellow. Same colors are used to show the results for the higher maximum stress level of 45%. The minimum stress level was unchanged. On both stress levels, the viscous cyclic strain in blue is higher than the creep strain at mean stress level, and instead closer to but below the creep strains at maximum stress level in yellow. Comparing both diagrams, it can be seen that the distances between the curves remain constant for both stress levels. In summary, I have shown you in this presentation that for normal strength concrete with specimen moisture of approximately 100% under cyclic loading with maximum stress below 45%, viscous cyclic strains are higher than creep strains due to creep is equal to S mean. Instead, viscous cyclic strains are closer to but below the strains due to S creep is same as S max, which contradicts with the model given in FRB Model Code 2010. Therefore, further research is required. Several investigations are already ongoing. The cyclic influences such as stress, amplitude, and frequency were investigated, and the results are meanwhile published in the International Journal of Fatigue. In the next steps of this project, additionally, the pore moisture contents of specimens are varied, and the test duration are extended to create a broad database. On this basis and the basis of existing models, this will be continued by developing further model approaches for strains due to cyclic stresses. That brings me to the end of my presentation. In the name of all authors, I would like to express our gratitude for the financial support of this research project funded by the German Research Foundation within the collaborative projects linear and nonlinear cyclic creep at defined moisture conditions and creep and shrinkage under variable hydric stresses, in cooperation with the Wuppertal University. Furthermore, I would like to thank you for your attention and invite you to contact me via email for further information. And I'm open for your questions now.
Okay, thank you very much, Bianca, for your presentation. Very interesting topic. And now we will start with some discussion. Maybe I will just ask you, I will start with one question. You mentioned that you made all these experiments on specimens C25, 30, and did you made some experiments also on other concretes, or what would you expect if, for example, you will use the higher strengths of the concrete, for example, some high performance or ultra high performance concrete, how it will be changed or different from the results you get?
Yeah, we decided to do the investigations on normal strength concrete because of the because normal strength concretes normally have higher strains, and we're on a very low stress level. So we thought that this would be that the results will be clearer at this concrete, but I expect the same for HPC or
yeah. High performance concrete, yeah.
Yeah.
Okay. So maybe because I looked to the what will be the future continuation of the research, and there was not this mention that you will try also to check how it will be in the different types of concrete. So maybe this is one other task what can be checked how it will be. Really, it is the same.
Yeah,
okay.
I think that is very interesting, and I think this could be one further step.
Yeah. Okay, thank you. So please, Michel or Nicola, have you some questions?
Yes, thank you very much for your presentation, Bianca. And I find it extremely interesting, this research, because we know that we have observed on actual structures very large deformations with creep, and which were going far beyond what we would have expected. And I suppose that this research is giving an explanation to that, at least a tentative explanation. And I wanted to ask you if of some application of these results to actual structures to explain the results that were observed.
I'm not quite sure if I got it right. So the application for structures.
Yes. Yes, to try to explain why we were observing on structures, on some structures, deformations that were much larger than what our computation would have considered, would have indicated.
Yeah, I think there are several reasons, but one of the reasons is that all structures, especially bridges, are just calculated for constant stresses, but there are also traffic, which is a cyclic load, and there is in literature there's often mentioned that it might be a reason that the superposition of a constant load and a cyclic load leads to higher deformation than expected, and yeah, that was my motivation.
Do you know any example where this could this has been applied and could explain the situation that that exists?
Yeah, so till today, it's normal to just calculate bridges with a mean stress level and not the cyclic load.
Yeah, yeah, yeah. Okay, and yeah, and this your research and others will probably help explain why we are finding some larger deformations often. Yeah, very good.
Okay, Nicola, do you have some question?
Yes, so very interesting, and congratulations, and very interesting, and I think good contribution of the work. Maybe connecting slightly to the previous question, I thought it was very interesting for me to association. I saw previously some studies by actually Professor Peter Mark, for example, from Bochum. They were doing something similar, but on the level of deflections in terms of precisely this kind of effect of determining, you know, the quasi-permanent load. So kind of what is the proportion of the, let's say, this cyclic load that is then can be considered as this quasi-permanent. So this is somehow what your results maybe point to. Do you agree? Like, because you have your result below the, let's say, maximum, but then you can calibrate kind of which percent of this maximum is actually the cyclic load. So do you see it somewhere in that direction going and or being useful? And the second question in terms of this, like what was the rationale behind choosing the frequency of 0.1 hertz?
Yeah, so I will start with the first question. Yeah, I think so. When I developed the modeling, I also saw some other models in the literature, and I think the most interesting is the one of Bajant, based on the Paris law. And he has the idea that additional to the creep on the mean stress level, there's an additional strain due to micro cracks. This model fits not perfect for my data, but I think it might be the right way to say that there's an additional strain.
So do you see it in the future terms expressed in terms of like the maximum, like in a percentage wise respect to the maximum, or in function of the mean of the cyclic load? What do you think is a kind of better?
I think it will be a function of the mean and additional strain based on the stress amplitude and the frequency or the number of load cycles.
And in this regard, this choice of the frequency for the study, how is it derived?
Yeah, I choose very low frequencies. I also chose a frequency of 1 Hertz for further investigations because it's more realistic than higher frequencies. And higher frequencies also lead to an increase in temperature, which was presented yesterday by Martin Markert.
Okay, thank you. Thank you very much. I think Professor Hayek, we still have some questions in the Q&A.
Okay, so I have maybe one more question related to the previous. So the results are very interesting, and you mentioned the motivation, but do you have also with your colleagues or supervisor some idea how to implement it to some standards to make the calculations and analysis more precise and so on? Is there some idea to contribute in this way?
Yeah, definitely. I want to go into the modeling in the next steps, and then give this to the standards. Yeah, like I mentioned before, I'm working on a model based on an additional strain due to the cyclic loading.
Okay. Okay, perfect. So are there some other questions from panelists?
We have Professor Hayek both in the chat and in the Q&A.
Yes.
Do you want me perhaps to read them to Bianca?
Yeah, please.
Okay, so there is a question in the Q&A by Omi. Are experiments planned for longer time periods to better study creep?
Yes, we're doing actually investigations for a time period of 90 days.
Okay,
so also with cyclic loading.
Okay, so Omid, I think this answers your question. Let us know. And you have in the chat from Professor Farid, thank you for your presentation. Did you measure the temperature during the cyclic creep tests? We observed an increase of 10 to 20 degrees in some tests. It seems that you have performed only one test per cyclic creep experiment. There is some variability.
So I didn't mention the a temperature increase because of the very low frequency.
Okay, and this about the variability, was it one test per cyclic creep experiment?
Could you repeat the question?
It seems that you have performed only one test per cyclic creep experiment. Is there some variability? There were more specimens, or because you showed the gray area, for example, you said it's between these, but is this an average of several, or is it one specimen?
It's a mean of 3 tests per curve.
With some, let's say, significant variability between them that you saw, or pretty uniform results among the 3, let's say?
The tests were strains were very close to each other, so there's...
Okay. Professor okay, yes, says thank you.
Okay, so thank you very much, and thanks also to Nicola to remind me about the Q&A. And if there is no other questions, if not, so I would like to thank to Bianca Kern. So thank you very much. It was very interesting, very nice research, and we wish you success in finalizing of your work, and maybe you can extend it to other researches in this field. So thank you very much, and we can continue with other presentations. Okay, thank you.
Thank you.